How do we know when a reaction is at equilibrium? In general, the Gibbs free energy change for the reaction can be written in terms of the Gibbs free energy change for the reaction done at standard state, plus this correction which involves the reaction quotient for the reactants and products not being in their standard states. We know from the second law that when the Gibbs free energy change is equal to 0, that implies that the process, in this case the reaction, is at equilibrium. If we apply this to our equation for the delta G of reaction, we can derive a useful expression. At equilibrium, delta G equals 0, and therefore 0 equals the delta G for the reaction done at standard state plus RT times the natural log of Q for equilibrium concentrations. Notice that when the reaction is at equilibrium, the value of the reaction quotient will be one particular value. There is only one value of the reaction quotient that provides a delta G equal to 0. We call that one value of the equilibrium quotient KEQ, or the equilibrium constant. We can rearrange this equation to give us this very familiar equation from freshman chemistry again, where the equilibrium constant is related to the standard state value for the delta G of reaction. Let's take a look at this from the microscopic point of view. Remember that the Gibbs free energy, it can be written in terms of the partition function as minus k Boltzmann T times the natural log of the partition function, where Q in this case is not to be confused with the reaction quotient, but rather is equal to the partition function. Since delta G for the reaction is equal to the Gibbs free energy of the products minus the Gibbs free energy of the reactants, we can write that delta G for the reaction is equal to minus k Boltzmann T times the quantity natural log of the partition function for the products minus the natural log of the partition function for the reactants. Using properties of natural logs, we can rewrite this equation in terms of delta G of reaction is equal to minus k Boltzmann T times the natural log of the ratio of the partition function for products versus reactants. If we look at this on a per mole basis rather than a per molecule basis, the Boltzmann constant simply becomes the gas constant, R. Now we can see that the ratio of the partition functions is simply equal to the equilibrium constant. As is the case with thermal equilibrium or mechanical equilibrium, chemical equilibrium will be reached when the system maximizes the number of microstates available to it. Notice that if the products have more microstates available to them than the reactants, then Q product will be larger than Q reactant and KEQ will be large. That is, the reaction will proceed towards products primarily. That will maximize the number of microstates available because the products have more microstates available than the reactants. Conversely, if the reactants have more microstates available to them than the products, Q reactant will be larger than Q product, leading to a small equilibrium constant and a reaction which does not proceed very far towards products and stays mostly reactants. Again, this will maximize the number of microstates available to the system because the reactants have more microstates than the products. So we can see that this ratio in the partition functions simply leads to a maximization of the number of microstates available at equilibrium.